Hi there. There were two things I wanted to tell you just to make sure I've completed the discussions from class on Wednesday. And I know a number of people dropped out of the class because of Wi-Fi at the end when I was describing these final points. And I just want to make sure you get them for the purpose of your lives more than anything, right? So you know how to read an electric bill or utility bill or what you're actually being billed for, and how to actually think about energy conservation. So that's the second part. The first part is quicker. I also wanted to show you the answer to number 4 on homework 1. Not give you the full answer, but show you where to find it. So in the textbook, I'm looking here at figure 1.3, and it's showing the energy per capita, right? We know when we're talking about energy per capita, it should be kilowatt hours. I just noticed that. There's errors all over the place. So they actually probably mean kilowatt hours here, because kilowatt is actually a power. But I digress. There are errors all throughout. This is probably a kilowatt hour. Anywho, this is the relationship between kilowatt hour and GDP, gross domestic product. So this is basically the amount of money a country earns, and I'll let the economists talk about this. It's total output of goods and services, as you see down here. As the GDP goes up, there's a point where the energy actually goes down. The energy per capita goes down, and that's the upside down relationship. So if you're looking in your text, I'm really looking at this part here. And I didn't pull it out to be obscure. It's the idea that the higher your GDP, the better and more efficient you are at actually making and using your resources and making energy. So in fact, the more money you have, the better you are at actually harnessing energy, and it actually costs less per person. Right? So when you look at this text, that's where I'm looking. So feel free to go back, and a number of you had either not answered, or either you didn't have the text or you did answer it but didn't see that reference. So feel free to redo that one. Okay, so describing conversions, electrical bills, etc. So I really want you to think about power versus energy. And really think in terms of rate versus unit. So power is a rate, whereas energy is a unit. It's a unit of measure. So what I mean by a rate always means some kind of unit of any kind per time. So as an example, a car might drive 60 miles per hour. That means 60 miles in 1 hour. This is a rate because you have a distance. That's our unit. It can be any unit, whatever you care about, divided by a time in hours. Therefore, this is the idea of a rate. But if you're driving 60 miles per hour, I have no idea how far you actually drove unless you tell me the overall time. So to get between a unit and a power, or a rate, so if we look on this side, if you take a rate times a time, you get the total unit. So if I told you, I asked you, well, let's say you were driving for 1 hour. How far did you drive? Well, you would say, if I drive 60 miles per 1 hour, 60 miles per hour, and you multiply it by that time, 1 hour, these cancel, and in the end you can say, oh, I drove 60 miles. So in 1 hour I drove 60 miles. That's our total unit. That's often what you want to know. The rate gives you part of the answer. Okay, so rate times time. Meanwhile, if you take your unit, divide it by your time, that gives you your power. Okay, so now that we know this, let's do this in terms of watts and joules. So let's go to watts and joules. So we'll keep this comparison going. If you have a 60 watt light bulb, again, that's a rate. That means you have 60 joules of energy in 1 second. That is what 60 watt, that is the definition of a watt. A watt is a joule per second. And a joule is a unit of energy. So a joule is the unit. Okay, so if you have a 60 watt light bulb, you'll have 60 joules per second. I don't know how much energy was used unless I know how long the light bulb was on for. So we need to multiply this by time the light bulb was on. And if we multiply it by time, then we will find out how much energy was used. So this brings me to kilowatt hour. So kilowatt hour, I made jokes about how annoying that unit is. It just kind of stuck because it became a useful number to use. So let's think about, I'm going to go down here, get some more space. Let's think about a kilowatt hour. That is what you would see on your electrical bill. And let's break it down. What does this actually mean? Kilo actually means 1,000. Watt, well, we know what a watt is. That's a joule per second. And you take this and you multiply it by an hour. So if I had a 60 watt light bulb and I want to know the energy per hour, let's say the energy for a whole day, not just an hour. Let's do how much energy is used for 24 hours. If I left that light bulb on all day, so we're going to actually break this down. First thing we need to do is turn it into kilowatts. So we are going to say we have a kilowatt, then we're going to multiply it by the 24 hours. So first, 60 watts, we have to turn that into kilowatts. Turn it into kilowatts. Then we are going to multiply that kilowatt by 24 hours, and this gives us kilowatt hours. That's the total energy for the day. So first of all, to convert to kilowatts, that's the same as dividing by 1,000. So the quick shortcut, whenever you divide by a number with a 1 in front, you can simply move your decimal point. And that's what we were doing with all of those larger units. So if I want to divide this by 1,000, That's the same thing as moving my decimal over by 1, 2, 3. Right? We're dividing it, so it's going to get smaller. So we're going to go 1, 2, 3. So there's a 0. We're going to add a 0 there to take that spot. So right now, I know that this is equal to 0.060 kilowatts. Now I want to know the time over 24 hours. If I multiply those two together, then I'm going to get 1.44 kilowatt hours. All right. Now the other way you can turn this into kilowatts is you could also say, because sometimes the conversions are not clean cut, right? The only reason we were able to move that decimal point so easily is there was a 1 here. So we literally just counted zeros. If there isn't a 1 there, it's not so simple. So the longer way that would work all the time is you would say, how many watts are in a kilowatt? And if you remember from these slides, right, kilo is 1,000. That means there's 1,000 of something in 1 kilo. Right? So there's 1,000. You start at 1. So whatever was here, if this was a watt, then there's 1,000 watts in a kilowatt. So we're going to use this idea as a conversion factor. Right? So I know that I want whatever number I want on top. So I want to know how many kilowatts. So I'm going to write 1 kilowatt, because that's the number I want to know in the end. Well, I know a kilowatt has 1,000 watts in it. So that's 60 divided by 1,000, and you would end up getting this number, right? It's the same as moving the decimal by 3. All right, so what do we do with this number? Well, if most electricity bills charge between like 10 to 20 cents. 10 to 20 cents per kilowatt hour. Now this is the cost, not the actual cost. That's the whole point of my class. So this is what it would actually cost the end consumer at that moment in time. We pay for lots of other stuff in lots of other ways. Okay, so the average I found whenever I try to do these mock calculations is 12 cents per kilowatt hour. So that's what I'm going to use. Of course, it will vary. So if I know we have 1.44 kilowatt hours, and I know there's 12 cents, or I can write this as $0.12 per kilowatt hour, that gives me 0.17. $. In other words, it will cost 17 cents to run a 60 watt light bulb for 1 day. All right, so hopefully that helps some in your daily life. I promise you'll use this someday, if not in my class. All right, so going back, I just wanted to make sure that we were okay with these final numbers. Because this is an energy per time, we got that meant that it was power. For number 2, the point is everything has a certain amount of energy. It doesn't matter how you use it. So if you eat it or burn it, you still get the same amount of energy out. Number 3, 500 joules. We want to divide. To get a watt, we need joules per second. So I divided 500 by 300 seconds, which is 5 times 60. That's how many seconds are in a minute. And for the last one, depends how much you move the decimal points, but the answers are either 8.5 petawatts or